Okay, now let's talk about the section 6. The homotopic version of a Cauchy's theorem and the simple connectivity. The homotopic version. The homotopic version of Cauchy theorem and simple connectivity. Simple connectivity. Cauchy theorem. In principle, Cauchy theorem says the integral of f with along the closed rectifiable curve gamma is equal to 0. Well, here there is a condition. If the winding number of gamma with respect to A is always 0 for all A in the complement of the domain G. Okay, when this happens, we have this Cauchy's theorem. Well, this one is, this condition uses the winding number. The condition is in terms of winding number. In this section, we're going to talk about a less general. This is a general situation. So in this section, we will introduce or discuss, we will introduce a less general. Less general means it's covered by this winding number case, right? It's covered by the case, but more geometric. More geometric condition. To guarantee we have to ensure the integral of f along gamma is equal to 0. Okay, so we're going to find a sufficient condition, but that sufficient condition is from the geometry or topology. Okay, geometry or topology. Okay. So let's check this. Let's first start from the general case. So if we have G is open disk, and the gamma is a closed rectifiable curve. In G. All right, so we have a boundary, and we have A, and then assume this is a curve gamma. For each S, in 0, 1, each S 0, 1, then you will have a gamma S. Right? You have a gamma S. For this gamma S, we use straight segment to connect A and gamma S. Okay, the straight segment, what is a straight segment? It's a T A plus 1 minus T gamma S. Here T belongs to 0, 1. When T is 0, that is gamma S. When T is 1, that is A. So it's like this direction. You push this gamma S towards A along this trace. Okay, and we call each point on this segment, this is a point Z, on the segment Z. Because this is G is an open disk, G is convex. G is convex. Any segment connecting 2 points of them belongs to itself. So Z belongs to G. For all ST belong to 0, 1. So for every S, you can get this segment, right? So we define what? We define gamma T of S to be TA plus 1 minus T gamma S. What does it mean? It means for each fixed T, this is a T equal to 0. Oh, sorry. Yeah, this is T equal to 0. The original gamma is gamma T equal to 0. When T is equal to 0, you only have gamma S. And the gamma 1 of S is constant. So it's like you shrink this a little bit. For T, like this way. Every time you shrink it, and eventually you will shrink to the point A. So we can draw this trace of gamma smaller and smaller towards the point A, towards the point A. Every time you shrink it a little bit. And this is possible because there is no hole. So this is a nice idea from the topology. How can we describe a set has a hole? So what is a hole? How to describe? How to determine a hole? So for example, you have this set, you have a point missing. This point does not belong to the set. Then we say this is a hole. I mean, from the common sense, we say this is a hole. Now, how do we clear it? It's like you have a rubber band. It can shrink to a point inside this set. This rubber band, you make it smaller and smaller. Eventually, if you can shrink this rubber band towards a point inside the set, it means there's no hole. But if this is a hole, when you shrink this rubber band, eventually it will be this missing point. Then that is a hole. Okay? So you shrink a curve to a point. If that point belongs to the set, it's not a hole. If that point does not belong to the set, it is a hole. Right? Okay, so that is the idea. To make this idea more detailed or more concrete, we have the following definition. So let gamma 0, gamma 1, both from 0, 1 to G be two closed rectifiable curve in a region G. Okay, then gamma 0 is homotopic to gamma 1 in G if there is a continuous function capital gamma with domain 0, 1 cross 0, 1, the square, to G such that first capital gamma S0 is gamma little gamma 0 of S, and the capital gamma S1 is little gamma 1 S. Here S belongs to 0 and 1. And second, when you have the initial point and terminal point, they equal to each other. So this is also a closed curve, okay? So for each t, it's a closed curve. So basically what we have, for example, we have a closed rectifiable curve like this here, and a closed rectifiable curve like here. And how do we say they are homotopic? You kind of have like a continuous layer. So every time this is gamma 0, like for example, this is gamma 0.25, this is gamma 0.5, this is gamma 0.75, and this is gamma 1. So you can move this, you can continuously deform it to the gamma 1, from gamma 0 to gamma 1. This is a continuous deformation. All right. Okay, so see, if we have gamma t from 0, 1 to G defined by the gamma t of S is equal to gamma S, capital gamma ST. So it's like this. So when you have gamma t, you have this level. Then each gamma t of S is a closed curve. Is a closed curve, right? Each gamma t. This condition guaranteed it's a closed curve. And gamma t forms a family of a continuous family of curves. So you have to be smooth. You cannot break. You cannot have the sharp corners or stuffs. All right. So that's the idea. Well, one thing we have to be careful. We only require capital gamma to be continuous. So gamma 0, gamma 1 are rectifiable from the assumption. But gamma t is not known, is unknown, is not known rectifiable or not. We have no idea. for this t strictly between 0 and 1. When it's strictly between 0 and 1, we just don't know if it like this intermediate step. We have no idea if it's a rectifiable or not from the definition. From the definition, well, we don't know. But in practice means we may have a construction. We have concrete construction. In practice, we will construct gamma t so that gamma t is rectifiable or smooth when gamma 0, gamma 1 are rectifiable or smooth. Okay, so in practice, again, in practice means our construction will satisfy this condition, but this condition is not required by the definition. Definition does not require or does not give us gamma t rectifiable or smooth. We just have a continuous stuff, that's enough. All right? Yeah. Okay, so if we have a homotopic, so if gamma 0 is homotopic to gamma 1 in G, we will write gamma 0 tilde gamma 1. Okay, gamma 0 tilde gamma 1. And you can see that it's not difficult. You can see that this tilde is an equivalent relation. What is the equivalent relation? Equivalent relation means three conditions. Condition 1, gamma is equivalent is homotopic to itself. This condition 2, gamma 0 is homotopic to gamma 1, then gamma 1 is homotopic to gamma 0. Condition 3 means if gamma 0 homotopic to gamma 1 homotopic to gamma 2, then gamma 0 homotopic to gamma 2. Right? That's a three condition the three conditions in the definition of an equivalent relation. You always have this. Well, it's not too difficult. The first one, you just apply the constant. Right? The first one, gamma is homotopic to itself. You just define capital gamma st to be gamma s. Then gamma is homotopic to itself. And the second one, if gamma 0 homotopic to gamma 1, then there exists a capital gamma st such that it is equal to gamma 0 s if t is equal to 0, gamma 1 s if t is equal to 1. Then we define what? We define gamma prime of st to be gamma of s1 minus t. Gamma of s1 minus t. Then you will see gamma prime of s is gamma s1 minus t. If t is 0, it's gamma 1. If t is 1, it's gamma 0. All right, and this is of course continuous, so we get gamma 1 homotopic to gamma 0. We say there's certain order because you have 1 and 0. There's an order about 1 and 0, so that's why we put gamma 0 first, gamma 1 second. And here with a simple check 1 minus t, we can change the position of 0 and 1. All right. Third, gamma 0 homotopic to gamma 1 homotopic to gamma 2. From the first one, then there exists a capital gamma st with the condition capital gamma 1, gamma 0 s t equal to 0, gamma 1 s t is equal to 1. Gamma 1 homotopic to gamma 2, there exists gamma 2, capital gamma 2 st. It's a gamma 1 s if t is equal to 0, gamma 2 s if t is equal to 1. Okay, then we can define gamma st is equal to gamma 1 of s 2t if t is between 0 and 1, half, 0 and 1 half. Gamma 2 s 2t minus 1 if t is between 1 half and 1. Okay, so we just rescale the parameter domain t. So it's like the first half we defined for gamma 1, second half we defined for gamma 2 by this rescale, and then the total will be the domain of gamma. And you clearly see this is from gamma 0 to gamma 1, this is from gamma 1 to gamma 2, so put them together is from gamma 0 to gamma 1, gamma 0 to gamma 2. Okay, they are still continuous. All right, so that's the equivalence relation proof. All the equivalence relation will be defined by these 3 conditions. All right. Next, remember we need a little bit topology, so we give the concrete definition of a convex set. A set G is convex if given any 2 points A and B in G, the line segment joining A and B, they write this way, from A to B. Well, this is 2 complex point. This is not interval. Again, this one is not interval. It's just line segment from A to B. Okay, it's not interval. Lies entirely or completely entirely in G. Every 2 points, you can always connect it and get the line segment in G. Then this is a convex set. And there's another definition for this convex set. Remember, there's a so-called convex combination, TA plus 1 minus TB. This is actually the representation, parametric representation for the line segment. The convex combination always belong to G if AB belongs to G and T between 0 and 1. That's the same thing. Yeah. In the discrete math, they like to use this convex combination. All right. So disk is clearly a convex set. Every 2 points, you connect them. The total line segment belongs to the set. And another a special case, not a special case, even more general case is that the set G is star-shaped if there is a point A in G, there's a one point A in G, such that for each Z in G, for each Z in G, the line segment AZ lies entirely in G. Okay, so in the star-shaped set, like this star, you cannot just randomly pick up 2 points. You actually have one special candidate, A. Every other point will be joined to this A. Every other point will be joined to this A. If this segment always belongs to the set G, then this is called star-shaped. It's really like a star, right? And of course, convex sets are star-shaped for sure, because convex set, any point can play the role as a role of A. Any point will play a role of A, but for the star-shaped set, it's not always convex set. For example, this one is not convex, because if you join these 2 points, they are not. The line does not lie in the G entirely. You have to get a detour to make sure that they can be connected. Okay? And sometimes we want to emphasize this A, so we will say G is A star-shaped. G is A star-shaped. A star-shaped means you have to choose this A as a special point, right? You have to choose A as a special point. If G is A star-shaped, and if you have a Z and W in G, for example, this is A. I have a Z here, I have a W here. What path will I choose? I will choose path from Z to A and from A to W, so that the whole path is entirely in G. So the path you see, this again, this is not interval. From Z to A, from A to W. This one is a polygon in G. It's a polygon in G, and it's connecting Z and W. Connect Z and W. And clearly, every 2 points can be connected by this way, so we know at least the star-shaped sets are connected. So you see here we have a lot of relations. So connected, if we have a Venn diagram, this is connected. And then we have a subset, star-shaped. And then we have the set, convex set. Right? This is a relation, relative relation about these definitions. Okay. Now let's make our observation, not this one, make our observation abstract. Remember that at the beginning, we choose a case G equal to open disk, and we use a straight segment between the center and the gamma s, we connected them, right? It's the starting point. And now we are trying to make this more abstract. So we have the proposition. Proposition 6.4 says let G be an open set, which is A star shaped. If gamma is the curve which is constantly equal to A. So it's just a constant function, maps all the points 0, 1, 2 to A. It's constant. Then every closed rectifiable curve in G is homotopic to gamma 0. Okay, every closed rectifiable curve will be homotopic to this constant curve, even though we call it a curve, but the image is just a point. Well, actually the proof is identical to this. Here we mention this A to be the center, but the disk is A star shaped, right? So the proof. Just define gamma st to be Ta plus 1 minus T little gamma s, and that's it. So, and here, this whole thing, this set, this combination belongs to G because it's A star shaped. So you can connect it, gamma s to A. So that's the usage of A star shaped. And remember, convex set is a special subset. Convex category is a special subcategory of a star shaped. So if you replace this G by a convex set, this is still correct. It's still correct. You actually prove a more strong, more general case. All right. Well, a point is like a 0. In the curve study, point is nothing, right? You have a constant curve, you have a point curve, it's nothing. So we will have the definition. If gamma is a closed rectifiable curve in G, then gamma is homotopic to 0. Like gamma homotopic to 0. If gamma is homotopic to a constant curve, right? Gamma is homotopic to the constant curve. Like constant curve, a point, it's trivial in the curve, like real curve theory. So that's why we consider it as a 0. And this will play the important role in our generalization, not generalization, in our discussion. We introduce a less general but more geometric. Why we say it's geometric? We geometrically see you shrink this curve to a point. You shrink the curve to the point. So that's the geometric meaning, or topological. Whenever you can continuously deform, that's a topological condition. So we will use this definition, homotopic to 0 condition, to restate the Cauchy's theorem. Okay? Okay, excellent. So we will finish, we stop this video at this moment. We will continue the discussion in the next video. Thank you very much. Okay, let me show you all the stuff. This is the first page. And the second page. Third page. And page 4. Okay, thanks.